is. All right. So here we are. This is cryptography. Here. We've done the first chapter last time, and it's going to be the second chapter today, and I'll show you how to hack the two-time pad, which is a project I was very happy about. I got that, by the way, from one of these supplemental books up here. Anyways, this is something that really happened to the Russians in World War II. Anyway, let's start with randomness. Randomness is really important. Many times in cryptography, you need to start with a random number, and yet, what exactly is a random number? How do you generate it? And how do you know if it's random enough? None of those things are easy. So we'll talk about random number generators and various considerations. Here's an old Dilbert about it, where you have a random number generator. It just gives you 9 6 times. So is that random or not? Well, how do you know? You really don't know. That could happen. So exactly what test would convince you something is random? It's not easy, and most people would say this is more random than that. Now, that's an interesting statement. You have to define what you're saying. This exact pattern of ones and zeros has one chance in 256 of happening, and so does that one. If this is what you mean, then this is not any more random than that. But when you look at this, you probably don't really mean exactly this pattern. You probably mean something like 3 zeros and 5 ones. And that description includes a lot of options, and this is much more likely than that. So you have to consider what you're talking about more carefully than this to decide if something's random. So one way to do it is with a probability distribution. If you flip a coin, you have 50% chance of heads and 50% chance of tails. If you roll a dice, you have 1/6 chance of all the numbers 1 through 6. So those are a fair random probability. That's a uniform distribution with an equal chance of every outcome. All right, so it turns out the best way to measure this is entropy, which Shannon figured out decades ago, mathematician. So you have a distribution with n possible outcomes and a probability of each outcome, and the entropy is minus p log p1 minus p2 log p2 and so on, where the log is to the base 2. This is called the Shannon entropy. It is closely related to the thermodynamic concept of entropy, which measures the amount of disorder in something like a gas or a fluid, and it turns out to be a good measure of the information content of a computer file. So if you have one bit that could be 1 or 0, that's probability half and a half, and so the entropy is minus 1/2 log 1/2 twice. The log of 1/2 is minus 1. So that's minus 1/2 times minus 1, minus 1/2 times minus 1, so that's 1. So if you have one bit that could be either 0 or 1, the amount of information it contains is 1 bit. So it's making sense that far. If you have a random byte with all 256 possible values, then you have 256 possible values, each with a probability of 1 over 1 to 256. So if you do that, it's going to give you 256 terms that are 1 256 of minus 8, that's going to add up to 8 bits, just like it should. So a random byte has got 8 bits of information in it. And that's logical. Now, if it's not random, if it has a 99% chance of being 0 and only a 1% chance of being 1, then that does not contain as much information. In fact, it has almost 0 information, 0.08 bits, because there's no information encoded there. It's always just a 0. If you make 99.99%, then the entropy is 0.001 bits. So if you don't have any variation, then there's no information in there. It's just like a sign painted on the wall. So you can do these calculations with Python if you want to, but it's simple enough to just do with a calculator too. All right. Anyway, so let's start with a Kahoot. Let me get one up here. If you can handle, that's a little bit of math. Like I say, there's a little bit of math in this course and a little bit of Python, but not very much of either. Uh-oh, I don't think that's what I want. Let me go back. I want this one. All right. There we go. 141, 2A, there we are. Not that, this. Oh, and I see some comments going by. All right. Well, people are joining there. Let me go back there and see if I can see these comments. Spin equals curl. Some doctor application there are AI applications of quantum computing. Yeah, well, a lot of questions. I don't know. I don't know about the AI implications of quantum computing. There may be, but I haven't heard of the 2D connected yet. But quantum computing is in its infancy, for lack of good hardware. So I think we don't really know quite what it can do yet. In 10 years or so, in 10 or 20 years when we actually have working quantum computers, then we will find out what they're good for. Right? Might be enough. Let's give it a shot. All right, so what is the log of 1/4 to the base 2? So that's minus 2. The log to the base 2 means what power do you raise 2 to get this number? So the log of 4 to the base 2 is 2, because you take 2 to the second power. But to get 1/4, you take 2 to the minus 2. So the log of, that's minus 2. All right, what's the entropy of one random bit? That's 1 bit of information. Entropy is equal to the information content. Not 8 bits in 1 bit, just 1 bit in 1 bit. What's the entropy of a random byte? Right, 8 bits in a byte. If it's random, all 8 bits are used. If you have a file and all the bytes are all the same, then it's not really using all the bits. The information content is lower, and you could zip it and make it smaller. Zipping it is just squeezing the air out of it. All right, what's the entropy of a single base 64 character? It's 6 bits, not a very popular answer. So let's talk about what base 64 is. I got a text document here to write. So if a base 64 uses the letters A to Z, capital and then lowercase, and then the numbers, and then 2 more symbols like plus and slash. It's for a total of 64 characters, and that's all it uses. So instead of using all 8 bits in the byte, it only has 64 possibilities, not 256. And the purpose is to move binary data through email. Email is a text-only medium. It cannot move a byte. It can only move a printable character, and the first bit of the byte is always 0, or it's a constant value based on keeping the parity even or odd. So the point is, this is a way to encode data, but each character only encodes 6 bits. There's only 64 possible characters. Instead of encoding 8 bits, 2 bits are wasted. So that's what's going on here. This fills 6 bits of the possible 8 in each byte. So the information content of base 64 is 6 bits in a byte. By the way, ASCII, printed characters, uses 7 bits, not all 8 of the possible 8. So ASCII text has an entropy of 7. Binary data that's been compressed, like a JPEG image, has an entropy of approximately 8. It's really using almost all the bits efficiently. But these other text media are not really using the bits very efficiently. They are not exploring all possible values, so they have less information in them than you could fit in there. So you could take base 64 stuff and you could zip it to make it smaller, and that would work, because it would turn it into binary data using up those extra bits that were just being wasted. All right. Just C, all right. All right, let's get to here. CCSF readers, I think you might know who that is from before. I'm not sure. All right. So, all right. Anyway, if you didn't get that math right, don't worry about it too much. It doesn't really matter. It's not essential to the course. We're not going to be doing mathematical proofs, but it's good to understand it if you can. Anyway, so let's talk about random number generators. There's random number generators and there's pseudo-random number generators. So what you'd really like is a real random number generator, something that actually produces real unpredictable values. And that would be nice. But that turns out you need special hardware to do that, and until recently, processors did not include that hardware. It has been added by Intel, but people don't trust it. So that's a problem. Now, you can make a hardware random number generator pretty easily. You have a resistor, you run current through it, and then you magnify the Johnson noise. The resistance of a resistor varies slightly because of the random motion of the atoms. So the current going through it with a battery put across it varies a little bit, so you just amplify that noise, and you'll get random stuff, although it's probably not perfectly random. For example, if you heat up your computer, it will vary more. And if you were to apply a strong magnetic field, you might even be able to sway it to zeros or ones more or something. So nothing is ever perfect. One of the things people say would be most perfect would be radioactive decay. Have a radioactive isotope in there and measure the particles coming off, because it's almost impossible to speed up or slow down a radioactive process. But anyway, that's a real source of entropy. Something really random feeding in, and computers typically don't have this. What they have is an algorithm to produce random bits from a source of entropy they get somewhere, where they try to take a small amount of random bits and amplify it into more pseudo-random bits. So randomness needs to come from the environment. You need something unpredictable out there. Typically what they do is make the user type or move the mouse because they regard that as fairly random, something like that. The quantum random noise generator, like I say, this is probably the most perfect physical source of randomness, is a random radioactive decay, but most people don't have that hardware on hand. So a pseudo-random noise generator will take a real random noise generator that gives you a small number of bits, and it will then run them through a mathematical equation to make more bits out of it. So these will appear to be random, although they really are depending on a smaller number of bits coming in. All right, so you receive random bits from the random number generator at regular intervals. This fills up an entropy pool. It mixes the pool's bits together and creates, goes through a cryptographic algorithm to create this stream of pseudo-random bits. Now, this uses the deterministic random bit generator, which takes some of the bits from the entropy pool and expands them into a longer sequence. If you get the same input, it'll make the same output. That's what's deterministic about it. All right, so it's going to have operations like initializing the entropy pool, refreshing it using fresh data from the random number generator, and just going to the next group of pseudo-random bits. So this is what we're doing, or at least what we were doing until recently in Linux. Here's the security concerns. One issue is forward secrecy. If I measure the random bits, can I guess what they were in the past? If I could find a pattern and predict it, that would be backtracking, or forward secrecy. Prediction resistant means it's impossible to predict the future bits from a sample of it. That's what you want. You want it to be impossible to predict the past or the future from any sample of these bits. That's what it would be to be sufficiently random. Now, the NSA knows that these properties are typically not there, and so they're betting on it. The NSA has for about a decade now been archiving all the data they can get off the internet, which is essentially everything, because in violation of the Fourth Amendment, AT&T has been handing everything on the internet backbone and the telephone backbone straight to the government unfiltered ever since 9/11. And they did it without court authorization, and when this finally came out about 10 years later, Congress passed a special bill forgiving them for it. The same thing happened in the UK. The UK, they're just spying on everything, and to hell with the rights because they're afraid of terrorism. The same thing happened here. So they have this giant data center, and there it is in Utah, that is archiving all the data from the internet, most of which is encrypted, but they're hoping that they will be able to find the key later. When they hack into some machine, seize a machine, or somehow develop the key by guessing, they're holding on to that data, expecting that the keys will be found later, and sometimes they are. And some cryptographic algorithms make that easier than others. In particular, TLS before 1.2 did not have forward secrecy. So if you could get somebody's private key for the HTTPS certificate, you could decode all the data that had been sent to them. Now, with TLS 1.2 and 1.3, every session has a separate key. So if they break into one session of you sending email or something, they don't get into any other sessions without having to break into them separately. But that was because of Snowden. Anyway, so to achieve these things, you have to have refresh, and next operations must be irreversible, so you can't predict them. And you must refresh it with fresh random numbers so it doesn't keep using the same random numbers and therefore become predictable in the future. Fortuna is one of the random number generators designed by Bruce Schneier and Niels Ferguson. And this is what Windows uses. Mac OS and iOS use something called Yarrow to do the same job. And so if the source of random numbers fails to produce enough bits, then Fortuna might not notice and just produce bits that are less random, or stop delivering bits. If you can steal the seed file, then Fortuna will produce identical sequences of bits. So there is a way to steal something that will let you predict the future in Fortuna. All right. Now, most random functions in programming languages like Java and Python are not that secure at all. They're considered non-cryptographic random numbers. They're random enough so you can use them to choose how a monster will move in a game or something. And they're random enough that if you want to have statistics, it'll have an equal chance of getting each of the numbers, but they're not avoiding being predictable. They're often using something called the Mersenne twister. For cryptographic purposes, you want an unpredictable random number generator, and you have to pick a more careful function. So this is the way it used to be in Linux until 2022. A student pointed this out to me a couple days ago on Mastodon. They're quite correct. The urandom would get data from the crypto pseudo-random number generator, and it always returns data. Dev-random would be blocking. It will give you random data, but if the entropy pool gets low, it will stop returning data. This was the way people used to do it, and you'd have to keep refilling the pool. Blocking, they say, turned out to be a bad idea. It sounds like a good idea to stop producing random numbers when you don't have enough entropy, but in fact the entropy estimate is unreliable and attackers can use up the entropy to create this blocking condition. And so people decided in practice the other one is better, that just keeps giving you numbers even if the entropy pool is too small. And I came across this myself when I installed some Apache Tomcat-based stuff for a hacking challenge. And it took 45 minutes to boot up my server. And I found out this is a well-known problem. When Tomcat boots up, it needs to make some cryptographic keys. And if you just have a headless server with no keyboard and no mouse, it doesn't have any source of randomness, so it takes forever to get enough randomness. You have to install this program called HaveGed, which creates randomness, and then it will boot right up. I couldn't believe this, but it's absolutely true. You have to install a special software program to create more randomness for it to work. And so this is something I used to demonstrate in this class. I can't demonstrate it anymore. This will let you see the entropy pool. You just cat proc sys kernel random entropy available to see the available entropy, and this will consume entropy. Just get me a lot of random numbers and print them out. And what happened when I did this, you see the entropy pool is like 1900, but then when I start using it up, I can quickly drain it down to 53, down to 1, down to 3. You can repeat this thing that just dumps out a bunch of random numbers until you use up the pool, and then it takes a while to recover. So if you add HaveGed, then it just stays up all the time, because HaveGed creates lots of high power valuable entropy, or at least what's passing for that, so the pool stays nice and high. A student tried this and said it doesn't work anymore, and we found the fix. This was overhauled in 2022. Now they have changed it so it always has 256 bits of available entropy and you can't drain it. And there are blogs talking about what they did, but anyway, they've now changed it so this doesn't happen anymore in Linux. So if your Linux distribution is not more than a couple of years old, it will no longer have that property of having the pool get drained. So in Windows, I've got a couple of random generators. These take entropy from a kernel mode driver, which is measuring something about the hardware. Intel decided to fix all this around 2012 because there were getting to be a lot of problems caused by a lack of randomness, so they put a hardware random number generator in the processor, which sounds like a great idea. The problem is the authorities have been caught poisoning random number generators too many times. Nobody trusts them anymore. Some people refuse to use this, assuming the NSA must have poisoned it, which unfortunately they very well could have. And here Microsoft researchers found out in 2007 that the NSA had apparently backdoored the elliptic curve cryptography random number generator in use at that time. Now, they didn't say they had proven that NIST intentionally put a backdoor, but they did prove that the mathematics of it meant that if you knew certain secret numbers, you could predict the numbers, and there was no reason to choose this algorithm when there were others that were much better. So they strangely chose to promote and make a standard out of an algorithm that had a potential weakness, and the only logical reason to do that is because they have the secret. This is what the NSA calls no bus, nobody but us. This is their official mission statement. They want to read all the mail and all the transmissions everywhere with some way that nobody else can use. They want to be able to break into everybody's private stuff, but nobody else should be able to get in. And as Bruce Schneier said on stage at TrustyCon, there was a con just to argue about exactly this, he said, poisoning the random number generator is probably the best way to do that. If you poison the random number generator and there's a secret way to predict it, and you keep it secret, nobody will usually ever catch you. It'll look random out here, everything will be fine. If you want this property of nobody but us, that is probably the best way to do it. And that appears to be what the NSA has done, although it has not been officially admitted or proven or anything, and it probably never will be. So Schneier wrote a blog about it, talking about this. This algorithm is 1,000 times slower than other options, and yet promoted by the NSA and made into a standard, and so all the cryptographers said, we better quit using it. This really looks suspicious. It really looks like this thing has been backdoored by the NSA. And the problem is, of course, Snowden. If the NSA could have that mission, and it might be a benefit to our security if they could achieve that mission, but if they can't keep their secrets, then suddenly it gets really hard to defend this system where they can break into systems, and then they leak out the secrets so other people can break in. Then they don't seem to be helping our security at all, and that's what happened. Snowden leaked out all kinds of secret documents, and what he did was he leaked out documents here that showed that they were, in fact, poisoning commercial systems. This is the worst case you can imagine. Insert vulnerabilities into commercial encryption systems and endpoint communication devices used by targets. Influence policies, standards, and specifications for commercial key technologies. They were absolutely doing this, pressuring private companies and lying to them to trick them into making standards that were unsafe so they could hack into them, try to achieve their mission statement. And this is the kind of thing that once it comes out, this causes people to lose faith in their government. So NIST formally chopped this one. They no longer approved it after it's no longer part of the standard. They were caught and humiliated for that one. So that's the issue. So Intel gave us a hardware number generator, but a lot of people refused to use it, just assuming it must be poisoned. Of course, I don't know where this paranoia would stop. You have to trust something somewhere, but the purists prefer completely open source things where the code comes from some other country and can be audited and didn't pass through official government approval. Now, if you want to do business with the US military, the US government, you have to use the standard government approved protocols. But if you don't care about that, a lot of people prefer to not use anything the US government has approved, hoping they're dodging the US government's backdooring of it. It is an interesting issue, and it goes on and on. So here's things that can go wrong. If you don't have enough entropy, this happened over and over again. Programmers didn't understand all this stuff we were talking about, so they would just try to find something random enough, like count the number of cycles since the power was turned on and add the number of key presses the user has given so far or something that seems random enough. This turned out to be a pretty bad idea. They tried to seed it from the process ID and the system time. I've seen a ton of this in Android apps where they try to create a key by taking the user account name for this app when it was installed plus the system time or something to make a random key. You can try that, but it's for amateurs. None of these are really random enough. Then this one got everybody. In 2015, there was a researcher that tested all the public HTTPS certificates. Now, HTTPS certificates are based on RSA, at least they were at this time, so they're the product of two random prime numbers. And now you can't reverse the product and find the prime numbers, but if you have two things that share a prime number in common, it's very easy to show that. So they just took all the 7 million public keys and tested to see how many of them have used the same prime number, and it turns out a lot of them, thousands of them, have the same fundamental prime numbers. Now, how could that even happen? There was all kinds of arguments for a couple of years about how this could happen, but the end explanation that won was this. They were just firewalls, for example, a whole line of firewalls, all with identical hardware. They will boot them up, they start the boot up process, they reach a point to generate the key, they pull the randomness, they're exactly the same hardware, they've been up for exactly the same number of microseconds, they have a pretty high chance of generating exactly the same so-called random number, because there's no real source of randomness anywhere. So that's what they say happened. They would go through a process like this and end up choosing an identical P or Q some percentage of the time, like 1 in 1,000. It really is a problem when you can't really have random numbers. So generally people use non-cryptographic pseudo-random number generators, and this is something you find a lot of source code. People will say, here I just used some random function that was handy, and I understand that you're supposed to use some better function, but I don't know what it is, and somebody else will have to fix this later. This is in a lot of products that ship, because a lot of programmers don't understand cryptography, and a lot of them have no idea, they don't even know what they don't know, so they just do it wrong. Some people do know, I don't know enough, but at least they put a note in, some cryptographers should fix this later. But it's a big problem. And so CryptoCat was a tool used during Arab Spring for people to protest their government in Arabia. They were using unencrypted Twitter at that time, and they were getting captured and tortured and stuff. And then this guy rushed out this product called CryptoCat, which was supposed to be safer, but he was pretty clumsy in the cryptography. He didn't do a very good job, and people yelled and screamed at him. But it had various errors. Well, I say it's not. He said it's still better than unencrypted Twitter, which is probably true, but it wasn't very good. Anyway, all right, let's try another Kahoot. All right. Oh, let me check for comments in the Twitch after I get this loading. All right, let's see. Yeah, you can play it with 2 hours. Yeah, you can, but not. Yes. And I think I might even have some of those projects in this class where you do it. You'll see what it can do. You can do a few things with it, but you can't do enough to do anything new with it yet. It's in very early prototype state. Probably just the wind blowing, the window shut, I suspect. The wind is real strong around here. I guess we got the people that are coming. All right, so which item harvests entropy from keyboard and mouse input? That's the random number generator. That's truly random. You have to have some source of randomness from the outside world. All right, which one will update the entropy pool? It's the pseudo-random number generator. that harvest data from the random number generator to fill a pool of entropy, which it then calculates pseudo-random numbers from. And what algorithm does the Mac use? Which I assume is named after the yarrow stalks you're supposed to use to cast the I Ching, which is an ancient random process. Anyway, Anderson. Sure. All right. So let me stop this recording.